Hello everyone, welcome back to Mitchell's Physics Review. Today we are looking at motional EMF. Let's take a look at our problem. Two parallel rails with negligible resistance are 11 centimeters apart and are connected by a resistor of resistance R3, which is equal to 5 ohms. The circuit also contains two metal rods having resistances of R1, which equals 12 ohms, and R2, which equals 15 ohms, sliding along the rails. The rods are pulled away from the resistor at a constant speed of V1 equals 4 meters per second and V2, which equals 2 meters per second, respectively. A uniform magnetic field of magnitude B equals 0.01 teslas is applied perpendicular to the plane of the rails. Determine the current in R3. So, to start, they gave us a lot of information, so that we may be able to conceptualize it and understand it better, let's redraw the given picture, but this time, let's label everything they gave us. So, R1 is given to be 12 ohms, R3 is given to be 5 ohms, R2 is given to be 15 ohms, V2 is given as 2 meters per second, V1 is 4 meters per second. We're given that the magnetic field is pointing into the page and that the magnetic field's magnitude is 0.01 teslas and that the length is 0.11 meters. At this point, you might be a little lost about how we would find a current from this setup. Usually while looking for a current, we have some type of circuit. Well, as a matter of fact, this is a circuit, we just have to look a little harder. Since these two metal bars are moving through a magnetic field which is perpendicular to them, there should be an induced EMF within them. So, to start, let's find that induced EMF. We know that induced EMF is B times V times L. So, we were given all three, the magnetic field, the speed, and the length. So we can plug in each one to find the induced EMF on each bar. Let's start with the EMF on rod 1, or the rod towards the left. We can plug in the magnetic field, the speed of 4, the length, and we get EMF 1 equals to 0.0044 volts. And if we do the same process for EMF 2, we find it equals 0.0022 volts. Now that we have identified an induced EMF and have calculated it, let's take a step back and look more into what the currents would look like now. Since the field is pointing into the page, by the right-hand rule, we will find that the current is moving counterclockwise in both the left and the right rod to create a magnetic field out of the page to make a net zero. Now before we start getting into any of the math, let's just start by setting up what this circuit diagram would look like so it's easier to look at and conceptualize. Let's start at the leftmost loop. We have the EMF that we just calculated of 0.044 volts. And since it's going to be flowing counterclockwise, we have a positive terminal here and a negative terminal here. Then we have our 12 ohm resistor. For I3, we have our 5 ohm resistor in this middle branch. Then we have our 15 ohm resistor, and we have our EMF2 of 0.0022 volts. Remember, both these currents are also going counterclockwise from our previous statement of how the induced current would create an opposing magnetic field. Now, let's take a step back even further before we jump right into the math and find out why is this current going upwards. Well, we know that the current is equal to EMF over resistance. And in this case, the EMF through this branch here is greater than and the resistance is less than the resistance in this branch and the EMF in this branch, which means I1 will have the stronger current, meaning it will push through and make I3 be going upwards. Now, for everybody's favorite part, we are going to use Kirchhoff rules to write our three equations to solve for the currents. So let's start with this leftmost smaller loop. We start with the EMF, or the battery, so negative to positive, which is 0.0044, because we know going from a negative potential to a positive potential is a gain. Then across this resistor, we have I3 times the 5 ohm resistance, but this time subtraction because we're going from the positive to the negative. Similarly, we have I1 times 12 ohm resistor, also subtraction because we're going from the positive to the negative, which equals to 0. Similarly, we're going to do the same process for this rightmost loop. We're going to go across the EMF or battery and we get a positive 0.0022. Then we're going to go to this resistor and we subtract I2 times 15. Once again, we're going to positive negative there, that's Y. And then we have a gain as we go across this resistor and the middle branch because we're going from a negative to positive. So then it's I3 times the 5 ohms, or plus I3 times the 5 ohms, equals to 0. And then finally, ignoring this middle branch completely and going throughout, we'll start at this side. We go from a negative to a positive, so plus 0.0044. We travel around, get to this battery, negative to a positive, so plus 0.0022. We make it to this resistor right here, positive, negative, so we subtract I2 times 15 ohms. We make it to this resistor here. We see it's positive, negative, so we subtract I1 times 12 ohms and set it equal to 0. And finally, to help us out for when we plug this onto our calculator, let's take a look at the junction rule and find that both I1 and I3 traveling inwards are going to be equal to I2, the resulting current. So now that we have the three written rules and the junction rule, we can plug them all into our calculator and solve for I3, which is 126 microamps. Overall, the hardest part of this problem for me was finding the circuit. I didn't really understand that the moving bars would cause the induced EMF, which would cause the current to go in certain ways. So what really helped me and what really counted was breaking down the circuit into each individual parts and looking at what we know, and also trying to remember and review what we've previously learned about the EMF. Once I did that, it helped me realize that there was going to be an induced EMF, which would help us create or draw our new circuit diagram, which helped us write the rules and solve for current. I hope this video helped you as it helped me. Have a good day.